I've been getting a lot of questions about circular motion. And so I really want to emphasize that a lot of your learning for circular motion is already in place, and it comes from what you studied about linear motion. There's a way in which you can take circular motion and you can unpack it into linear motion. Now, while it might look different going in a circle versus moving in a line, so let's say you have a circle. Let's say you cut it with some scissors and you took it and you stretched it out like this. Now you have a line. So you are still exhibiting linear motion as you move around a circular trajectory. So how do we unpack that? Well, we have to ask ourselves two questions. One, what is the angle that is being swept as I move about this circular motion? And two, how far away am I from the center of the circular trajectory? Because here's the thing. If I was to sweep a little bit of angle like this, and instead I doubled how far away I was from the center and swept the same angle, I would cover more linear arc out here than I would here. And so this is the key. What you need to do to figure out how much linear arc. So if you imagine a circle that has a particular radius, it has a circumference. And so how much distance are you traveling around that circle? We want to figure out what that distance is. We have to know both how far away from the center of the circular trajectory you are, that's the radius, and we also need to know how much angle is swept per unit time. So here's the thing. The amount of sweeping, if you will, is theta, okay? And so you can think of that as the rotational analog to when we have this idea of displacement, but you can take theta and also multiply it by the distance away you are from the center, r theta. That r theta is what actually gives you the arc length. So it's not enough just to know how much angle is swept. You have to also know how far away you are from the center. So when you think of the concept of displacement, right, if you have a point A and a point B and the distance between point A and point B, the circular analog for that would be r theta. And so just as we have the concept of displacement over time, remember that? How much distance change versus how much time change, that's velocity. There's also the rotational analog to that. So the radius r and the angle that's swept, right, that is your rotational displacement. But then you can also think of, does the rate at which I'm sweeping angle, does it like start and then go faster? So the rate at which your sweeping angle can change over time. Delta theta divided by delta t. And the symbol that's used for that is omega. Okay? And so you have the arc length swept, that's r times theta, and then you have the angular velocity, as it's called, which is delta theta delta t, that's omega. And so in addition to having a certain amount of arc length swept, or a change in the rate in which that arc length is being swept out, you also have the idea that the angular velocity can change. Just like we know that regular velocity can also change. It can go faster or slower. So the change in velocity over change in time is what we call acceleration. Similarly, when it comes to circular motion, omega, the angular velocity, can change over time. And so we call that alpha, okay? And that's the angular acceleration. So here's the thing. A lot of your learning has already taken place. For example, all of those equations that you learned for linear motion, if you make a simple substitution where if you have a particular displacement, right, like delta x, if instead for a circle you substitute that with r theta. Now, if you have a velocity term in your linear equations, like the letter v, well, the rotational analog to that is going to be the angular velocity, omega. Okay, so where you see the v's in your linear equations, you now are instead going to use omegas. And when it comes to the acceleration, the symbol A that you see in the linear equations, the rotational analog for that is going to be alpha. So you actually already have the equations. Now what you need to do is you need to substitute, whether you're talking about thetas or omegas or alphas. And what you're doing is you're just simply taking this circle and you're cutting it and you're stretching it out, and you're seeing how much of that linear distance changes over time, or how much the change in linear distance over time changes. And so you just now have to account for the fact that when you're in a circle and you're sweeping out some angle, you also have to account for how far away are you from the center of the circle. Because for the same amount of angle being swept, a shorter radius is not going to sweep out as much arc as a longer radius. Okay, so now another batch of questions I get is with respect to centripetal force. And so for centripetal force, assume that we're moving in a circle, and we are going to be moving in a circle at a constant velocity, and the radius of the circle does not change. So what needs to happen to satisfy those conditions? Again, I'm moving around the circle at a constant velocity, and the distance from the center of the circle is going to remain constant. What needs to be satisfied? So where the confusion lies is some people think it's kind of strange if you're moving in a circle, why your acceleration to keep you in the circle has to point directly to the center of the circle. This gets back to how we can sometimes have misconceptions about motion, in that we think that if motion is in a direction, there must be at least some force in that specific direction. And so why wouldn't some of it be in the direction of the actual circular trajectory? Why is it always perpendicular to the circular trajectory? And the reason is that if the centripetal force, okay, and the centripetal force, by the way, has to be supplied by something. Oftentimes what supplies centripetal force is friction, okay? And so if there's some friction, so imagine you were spinning around like on a merry-go-round, and imagine you have your feet dug in to the merry-go-round and you're holding on to a handle. That's supplying friction, which is supplying the centripetal force towards the center of the merry-go-round, okay? Again, centripetal force is not a force in and of itself. It's a description for forces that already exist in nature that happen to be acting towards the center of circular motion to supply the requisite centripetal acceleration to keep you in a circle. So here's the thing. So if you're moving around in a circle, so let's say I'm right here. And so I'm going to go up a little bit, right, to stay in the circle. Now, it turns out the centripetal acceleration is perpendicular to the motion. So like if I was to draw a tangent to that circle, well, the centripetal acceleration is perpendicular to that. And it has to be to stay in a circular motion. And here's why. So if I am, say, here's a tangent to a circle, and here's the centripetal force perpendicular to it that's pointing towards the center of the circle. Let's hypothetically say instead, like the acceleration is like this. Now, some component of the acceleration would actually be in the direction of the tangent, meaning that the velocity is now going to get some acceleration in this direction. If it's perpendicular, it doesn't, okay? If it's perpendicular, the velocity in this direction stays exactly what it is. But if you have any component of the acceleration that is acting in this direction, it's going to go faster in this direction. And so what happens then? You no longer have a constant velocity, and you move a little bit from the center of the circle. So you no longer are staying at a constant radius. So that's the key here, is that to satisfy the conditions that the circular trajectory has a velocity that is constant, and that it is constantly at the same radius as it keeps going round and round, the acceleration must be perpendicular to the trajectory at any given moment, okay? So if you imagine at any time you're going around a circle and you draw a tangent to it, then the force itself, and therefore the direction of acceleration, has to be perpendicular to that tangent. Otherwise, you're not going to have a perfect circular trajectory anymore. So when it comes to centripetal force, even though you're moving around in a circle, remember that the direction of motion isn't always the same as the direction of acceleration. And as it turns out, the centripetal acceleration has to be perpendicular to the motion to keep it in a perfect circular trajectory of velocity v and radius r. And one more time, what supplies centripetal forces? It's not just that, well, this wants to be in a circle, so there's this new thing that we're going to call centripetal force. No, centripetal force is a name that we give to existing forces in the world that happen to supply the requisite centripetal force necessary, and therefore the requisite centripetal acceleration necessary to keep it in a perfect circular trajectory. I gave the example of a merry-go-round and how the contact between the soles of your shoes and the merry-go-round surface, in addition to probably holding on to something, together that gives you enough friction that is oriented towards the center of the merry-go-round's rotation to keep you on the merry-go-round. Another example would be, say, a string. So let's say that I have a string and I attach a ball on the end of the string and I start twirling around in a circle. So it's not some new thing called a centripetal force that's keeping the ball in the circle. It's an old thing called tension that comes from the string. It's the tension in the string that happens to provide the requisite centripetal acceleration. And again, when I'm talking about the requisite centripetal acceleration for uniform circular motion, it means that the velocity remains the same and the radius of the circular trajectory remains the same. But it's the tension in this example that is providing the requisite centripetal acceleration and therefore requisite centripetal force, not friction like the merry-go-round example. Okay, so centripetal force is not some thing in and of itself. It's just how we describe certain kinds of forces in nature that keep things moving in a circular trajectory. So one last thing, there's been some confusion about the distinction between a centripetal force and a centrifugal force. Turns out centrifugal forces are things that we perceive but actually are not the case, because it turns out that if you have an external reference frame and you're looking at circular motion, you have acceleration towards the center of the circle, as I've been saying. But sometimes we get the sensation that there's actually something pulling outward that wants to make us fly off of the circular trajectory. So the way you think about this is that it's not so much that something's pulling you off, it's that you are holding on to have just enough, say, friction to keep your acceleration oriented towards the center and to be at an amount that is v squared over r. Like if you don't have enough, say, friction to supply the requisite centripetal acceleration, then you do fly away. But it's not something pulling you, it's not having enough pulling you in. That's the key, okay? There's a difference between feeling like you're being pulled outward and whether or not you actually have the requisite inward to stay in a circular trajectory. And so one last time, when we're talking about uniform circular motion, the acceleration is always inward towards the center of the circular trajectory. To satisfy the velocity remaining the same, you have to have a constant radius and you have to have a constant angular acceleration. And when it comes to the requisite centripetal acceleration pulling you towards the center for uniform circular motion, if you have that constant velocity and constant radius, then you can simply say that the requisite acceleration towards the center of the circular trajectory is v squared divided by r. Sorry, I got in a little bit to equations here, but I hope that this explanation can allow you to get beyond the equations of circular motion to have a little bit better conceptual understanding of it.